Our topic is a tool in designing controllers and observers using state space methods, and the tool is called Ackermann's formula. This video contains motivation behind Ackermann's formula and the particular equations that we use for the method, and then a lengthy example of using Ackermann's formula, followed up by a summary of what was in the video. There are many instances whenever it is desirable to work with a state space representation other than either the controller or observer canonical forms. So for example, it could be that some different state variables are easier to measure in the physical system than maybe the phase variables, state variables would be. The problem is that the calculations for the gains can be difficult if one is not using one of either the controller or observer canonical forms. Ackermann's formula allows a person to design a controller in the corresponding canonical form and then transform these calculated gains to the desired state space representation. And these next slides introduce the equations and the notation that we'll use. We're going to say z bar is the state vector for the desired state space representation. So this is what we want to work in, maybe because the state variables are easier to measure than other representations. So here are the state equations. Here's the state space representation, and I put this up mainly just to show the new notation. We put a subscript on the matrices to indicate which state vector it corresponds to. So we've got z bar dot is a sub z times z bar plus b sub z times u, etc., etc. Now we're going to introduce another state space representation, and this is one that we'll use to calculate our controller or our observer. And for that we have a state vector, we'll call it x bar. And like I said, then we'll use this state space representation to calculate the controller gains k sub x or the observer gains l sub x. And here's the state space representation using x bar, and you can see that the state input and output matrices have the subscript x indicating which representation they go to. Again, this is the same system but two different representations. And we're going to introduce this transformation matrix P to go from one state vector to the other. So here's P times X is equal to Z bar. The way that we can calculate the transformation matrix is with either the controllability matrices or the observability matrices. So if we're using the controllability matrices, we would have C sub mz, that's the controllability matrix for the representation with the state vector Z bar, times the inverse of C sub mx, which is a controllability matrix calculated from this state space representation. And you can also calculate P with the observability matrices. Now I'll skip over the step here, but say we had calculated the gains for our compensator, our controller, or the observer, and we did that with the state space representation X. Now if we want to get those gains to use for our z-bar state space representation, we could use the transformation matrix as shown here. So we get the state variable feedback gains k sub z by multiplying k sub x times inverse of p. And for the observer of the state space representation using z-bar, the gains L sub z would be p times L sub x. It might be a good idea at this point in the video for you to pause it and take a break. Next up is an example using Ackermann's formula. We'll start off this example given the transfer function for a plant, g of s. So we've got this third order plant with a 0 at -3. And we are also given the fact that we want to use the cascade form state space representation for this plant. So our task is to design a controller with 20.8% overshoot and 3/4 second settling time for the closed loop system. and then also to design an observer with 10 times faster response than this closed loop system. So the approach that we'll take is to write the controller canonical form of this plant and design a controller for it, then transform those gains back to this state space representation, and likewise write the observer canonical form for the plant, design an observer, and then transform those observer gains to this state space representation. First, though, we want to verify that the system is controllable and observable. Here is the controllability matrix for the cascade form. So we've got the first column is B, the next column is A times B, and then A times B. And the determinant of that matrix is -1, which is not equal to 0, so it's full rank and we have a controllable system. The observability matrix is given by this equation. Here's the first row is C, and then the next row C times A, and then the final row gives us our 3x3 observability matrix, which has a determinant of 16, which is not equal to 0, so it's an observable system. And it is thus possible to design controllers and observers for this system. As I said a second ago, our approach is to transform the controller gains designed for the phase variable, also known as controller canonical form. Here is that state space representation. This is a different state space representation for the same plant. Based on the transfer function given, we come up with the controller canonical form. So using this transfer function, get the controller canonical form or the phase variable form, and we're going to get the controller gains like we've done in previous videos for the pole placement method. So here is the formula for the characteristic equation. We've got the closed loop state matrix, and again we have the subscript x to indicate that it goes along with this representation. And here is that matrix, take its determinant, and we get this third order equation with our unknown gains for k sub x. And now we set that equal to the characteristic equation of a system with the desired transient response. And that's the 20.8% overshoot and 3/4 second settling time. In addition to, so we have 3 poles to place. The transient behavior gives us our dominant second order poles, and then the third pole we will put at -3 in order to cancel out the 0. The transient response corresponds to a second order system with damping ratio 0.447 and natural frequency 11.9. So those 3 poles together give us this characteristic equation. We've got s plus 3 to cancel out the 0, and then s squared plus 2 zeta omega n times s plus omega n squared, and we end up with this third order equation. And we want to set that equal to the characteristic equation from the previous slide. And for convenience, it's written here again. So when we set these two equal, we solve for k1 as 392, etc., and this is k sub x. So these are the gains for the controller canonical form state space representation. And in order to use the cascade form like we want, we need to transform those gains back into that state space representation. So we'll use the transformation matrix P to get k sub z. Now we need to calculate P, and we use the controllability matrices. So we got C sub mz, which we already found whenever we were verifying controllability. We need to find C sub mx, which is the controllability matrix using the controller canonical form. So the first column we have B from this, and then A times B will be the second column, so that'd be 0, 1, -13. And then the third column is A times B. So that's controllability matrix corresponding to our state space representation using X bar. Inverse of that matrix, anyway, we end up with this for the transformation matrix. And then now we can calculate the gains for the cascade form, our desired state space representation. Okay, so we've got the state variable feedback gains for the desired state space representation. Let me recap what we've done so far. We were given a plant transfer function and the desired closed loop response. We were also given the fact that we wanted to use the cascade form state space representation. So we wrote the state space representation for the plant in controller canonical form and computed the controller gains for that representation and finished up by transforming those gains back to the desired state space representation. So next we're going to do a similar process for the observer. We will write the observer canonical form of the plant state space representation and then compute the observer gains and transform those to the desired form, which is a cascade form. Here is the state space representation of the plant in observer canonical form, and we're going to use vbar for the state vector of this representation. Now to find the observer gains, we're going to use this for the characteristic equation, and this is the same process that we did for calculating observers in previous video. So now we've got A minus LC, and these have the subscripts V to indicate that they come from this state space representation. The determinant of this matrix gives us a third order equation with our unknown gains, and we just need to set that equal to a characteristic equation of a system with the desired transient response. That desired characteristic equation is for a system with a pole at s equals -3 to cancel the 0, and the dominant second order poles will be 10 times the second order poles for the closed loop system. Now we write the characteristic equation like this, and this is similar to the slide for the controller. We still had the pole at s plus 3. Now our quadratic, instead of having s squared plus 2 zeta omega n plus omega n squared, what we end up with whenever we multiply those second order poles by 10, we end up with this term is multiplied by 10 and this term is multiplied by 100. So it's kind of like s squared plus 20 zeta omega n plus 100 omega n squared if we're using zeta and omega n from the closed loop system. Anyway, that gives us this third order characteristic equation, and we follow the same process by setting it equal to this third order equation to solve for the gains L. And again, those are for the observer canonical form, so L sub V. And here are the values. This is a column vector, so we've got the transpose here. Now we just need to transform that to the desired representation. So we'll get L sub Z. So this will be an observer for the cascade form, our desired state space representation. And that can be calculated by multiplying the transformation matrix by L sub V. And one big important thing, this transformation matrix is different from the transformation matrix we used with the controller, because that was the transformation matrix between our controller canonical form and the cascade form. Or in other words, that was a transformation matrix from X bar to Z bar. Now we're transforming from observer canonical form to cascade form. Or in other words, we're transforming from V bar to Z bar. So we can't use the same transformation matrix as before. We need to calculate it again. Here's the equation for doing that. The controllability matrix for the system with Z bar that we already have, times the controllability matrix for this observer canonical form. And I left that off for this slide and instead just gave the result. Oops, this equation has an error. Let me fix that. Excuse me, in that previous version I had left off the observer gains L sub V. Okay, so we've got the new transformation matrix using the controllability matrix for the observer canonical form, and we multiply that by L sub V. And here is the new transformation matrix. It's different from the transformation matrix from X bar to Z bar. And we multiply that by the gains that we found up here, and it gives us the observer gains for our cascade form. So now we have the gains for controller with the desired closed loop transient response, and an observer with 10 times faster response than that closed loop system. This slide summarizes what went on in this video. We saw that Ackermann's formula provides a way to transform controllers and observers from one state space representation to another, and saw the equations for using that formula, and here they are again. If we were using the state vector x bar and the state vector to z bar representing or being part of the state space representation that we want to use. Okay, transformation matrix P to go from x bar to z bar. Here's how we calculate it, and then here's how we can use it for the calculated controller gains and calculated observer gains. And also in this video we had an example that started with the state vector z bar. We designed controller gains for x bar and observer gains for state vector v bar, and then transform those gains to the original state space representation.